Okay, it looks like the pizza line has died down, so we're going to go ahead and get started here. It's my honor to introduce our speaker for this week. This is Dr. Jennings. She started out with a Bachelor's of Science in Geology from Duke University, and after graduating, got a job as a physical science technician at the Pacific Arctic branch of marine geology in Palo Alto, where she investigated offshore geologic hazards. After that, she came to grad school here at CU Boulder with a home of INSTAAR, which we love, and began a 43-year career studying the marine evidence of ice sheets and ice-ocean interactions. She's now a senior scientist here and a fellow and director of the micropaleo lab here at INSTAAR, and using paleo record to understand how ice sheets respond to climate warming, which I think we're going to hear all about today. So, Ann Jennings.
Thanks, Katie. It's so nice to be here and to see all of you. And I'm going to try to explain a bunch of things to you today. No matter how far I get in this talk, there'll be a good ending that will make sense. So the motivation of the work that I'm going to explain today is about the Greenland ice sheet's sensitivity to climate forcing and how important that is for understanding what sea level rise rate can be in coming years, and also how that has changed in the past. And I use paleo records, and I'm going to be showing you paleo records from Baffin Bay, Marine Corps. The paleo record gives us a lot of scope for understanding large changes in temperature, for example. Like we can study ice sheets with experimental data and historical climate records, but not have such a large scope of change that we can see with a paleo ice sheet like the Laurentide ice sheet, which was really huge and then retreated in response to the warming from the LGM. So that's what I think is one of the biggest values of the paleo record, is that it provides scope. And the warming interval that I'm going to target is the LGM through deglaciation. And I'm going to stick with the Baffin Bay ice shelf, which has been an ice shelf that has been suggested and then refuted several times. And it's back again. And the decline of that, which is recorded in the Baffin Bay detrital carbonate events. So I thought, when I was preparing for this, I thought you might like to understand how does somebody get here? How did I get here and then have 43 years of work? It started when I was an undergrad. I got to go to sea on this boat called the RV Eastward, and we went to the Mediterranean Sea in 1978, and we were looking for turbidites. And that's because turbidity currents were destroying subsea cables, and so people were interested for a geological hazard. And so we did. It was quite funny to think back on how the technology was so rudimentary. Like we took pipes, piston core pipes, and we just drove them into the sediment without a liner or anything. And then we dumped the mud out onto rain gutters. Then we used a knife to cut them open and look for things like braided sand layers that would tell us we had a turbidity current. And then they just got dumped over to the side. And nowadays, they're so precious because it's so expensive to go to sea. And so they're taken in tubes of PVC pipe and archived, and people can keep coming back and requesting samples as new proxies come to light. So after I went there, I was trying to get a job after I graduated college, and I went to a GSA meeting in Golden. And I was terrible at interviewing. I had no idea what I was doing. I was trying to interview for a job. But I went to the icebreaker, and I met this guy, Mike Field, who was at the U.S. Geological Survey. And he said, submit an application, and he gave me a job. And so I went out there to California, and one of the first things that happened was there was an earthquake, a magnitude 7 earthquake, and it was on John Andrews' birthday, November 8th, 1980. He wasn't born in 1980, but it was November 8th. And fishermen were saying that the sea floor had been disrupted when they were dragging their nets along the sea floor. They felt these bumps and stuff. So we went to talk to them, and then we went out to sea on this ship, the RV Eastward. No, not the RV Eastward, the SP Lee. And we went out twice, and we surveyed the area here. And we found what we thought were these scarps. And here you can see these bumps on the seabed. Until we brought out the side scan sonar, which shows you what the seabed looks like in terms of elevation. And it showed that instead of scarps, you know, we're thinking earthquake, there's scarps. It was really liquefaction. Okay. Anyway, so we figured out that it was this seafloor failure on a 1/4 degree slope by liquefaction. And that was my first paper that I did with Mike Field and others. So before I came to INSTAAR, INSTAAR was super famous for studying the glacial history and quaternary history of the Canadian Arctic and especially Baffin Island. And then John Andrews decided that it would be a good idea to go offshore and look for evidence of the ice history from shelf basins that were close to the areas where the ice sheets grew and decayed. And he brought on Lisa Osterman, who was from the University of Maine. She did her PhD, and she's a foram specialist. And they worked together. And then this offshore work, so when I came in, I was part of that shift to the offshore work. And that's where it all started for me. So now I'm going to tell you about when I came, we were working on this really cool project called SAFE, Sedimentology of Arctic Fjords Experiment. And that was led by Jaya Savitsky, along with Charlie Schaefer, and they were Geological Survey of Canada scientists. And I came too late to go on the ship, but I worked on a core from Clark Fjord, where I found 9 forams, which was a little disappointing because it was what I really wanted to work on. And this is an example of one from the Petermann Fjord. So here you can see Jaya Savitsky, who later came to INSTAAR and was our director. So I'd like to mention the CSS, later CCGS Hudson, which was a storied research vessel that the Canadians had. And Hudson was just decommissioned in 2022, and people were really sad about that because when you go out on these expeditions and you're with the people and you have these experiences, it's a very emotional thing to find that the ship is getting stripped of all its gear and put out to be decommissioned. There's something super sad about it. This is a gorgeous picture of the Hudson. It's a painting that's at the Bedford Institute of Oceanography. And I took a picture of it there when I was there recently. And there she's in white because she's a Canadian science ship. And here she's in red because she became a Coast Guard ship. So here are some of the people that I'm going to tell that I was telling you were so wonderful. These two, Brian McLean, I worked a lot with Brian McLean, and he has since passed away. And Claudia Curry, she just died in December. They were really special people to me. And here you can see these two, Gus Vilks and Charlie Schaefer, and they were foram experts. I think Charlie is still around. Gus died a long time ago. But we have in our lab here, we have a lot of resource materials from them. So then I did a PhD, and my PhD project was on Cumberland Sound. And it was started out as a project where we were going to get a really long record of climate because it hadn't been glaciated for more than 60,000 years. And that didn't turn out to be the case. So what we found was marine evidence for a more extensive Laurentide ice sheet from studying Cumberland Sound. And that just sort of started me on this course where I'm working on how far did the ice go? All these ice sheets go in there, and looking for evidence of that. Here you can see this is something that I have done time and time again, is be in the core lab on a ship describing sediment cores and taking samples. This is just very consistent with my history. So here you can see this 1987 map of the Laurentide ice sheet. And you can see how these land margins are really well defined. But up here, because this is all based on the land record, there's not really much evidence and data offshore. And so here you can see Cumberland Sound. It didn't have ice in it. We found, so it's a greater than 1,000-meter deep graben, and it's underlain by Cretaceous mudstone. And the way we found that out is kind of a funny story. We were taking this core 31, and it got stuck in the bedrock. So we were trying to pull it out of the seabed, and it was actually making that huge Hudson rock. And we thought we might break the cable trying to get it out of there. But when the core came up, it had a chunk of the Cretaceous mudstone with native sulfur in it. And it was shown by palaeomorphs that it was Cretaceous. And here is this is a very important picture from the thesis because it shows you have the bedrock, and then you have this thing we called BUD, basal unstratified diamicton, which had to be proven to be till because this was an unglaciated basin, remember. So we had to show that the BUD contained erosive elements from glacial erosion of the underlying Cretaceous mudstone, which it did. And then overlying that is this sequence of ice proximal to ice distal sedimentation that was deposited as the ice retreated. So what we ended up with, instead of a 60,000-year record, was a Holocene or late deglacial record of ice retreat. Okay, so now what I would like to show you is that I have done a lot of work all around this area. These are all the projects that I have worked on. And I've showed you 0 and 1. And I can't talk about all of these for this talk. I'm going to just do 8, 9, and 10. But I want to recognize a lot of the people in this room did a lot of work with me and John, and we had a lot of fun doing these things. But we're going to stick with Baffin Bay. And in Baffin Bay, we're going to use these records to capture where were the LGM ice sheets, how far the LGM is last glacial maximum, how far out did they go, and when did they retreat, why did they retreat, how did they retreat. So I'm going to start with some definitions because not everybody here knows about ice sheet history and all those things. Then I'm going to tell you about all the different iterations of the Baffin Bay ice shelf. And then I'm going to tell you about an actual experience we had with an expedition to look at real ice shelf facies. So we know what bona fide ice shelf facies look like. And then the last thing I'm going to do is tell you about work that's still ongoing that just came in 2023 about the Baffin Bay ice shelf and what we're finding now. So here's some terminology. First, just look at this gorgeous bathymetry in Baffin Bay. You can see these beautiful trough mouth fans with the troughs leading out into these bulges of trough mouth fans on the margin. They're really big on the Greenland side and smaller on the Baffin side. And what is a trough mouth fan? Or how it's built by advance and retreat of fast flowing ice streams that move sediments toward the margin. And it's built over time with these repeated glacial and interglacial cycles. But how do we determine the ice sheet margins at the LGM? We use two kinds of techniques. There's geophysical techniques, like I showed you with the side scan and geophysical profiles. And that can tell you about the physical sediments and stuff. But in order to get a ground truth about the timing and the environments, you've got to go to sediment cores. And that's what I work on. Okay, so this is just to show you, this is from Expedition 400. It shows you a trough mouth fan, and you can see that it's built by repeated advances, building up the margin over time. But what we're after is just this one. The last time the ice left the shelf edge and came to an interglacial position, and this is the temperature. Okay.
Use that.
So I can just talk?
Yes.
Okay.
This one.
There. Okay.
Yeah, that's the microphone now.
All right. So I want to show you these ice streams. These are the fast flowing ice streams that drain the Laurentide. And the Greenland ice sheet is often left out of these things because it's not, the people that are working here don't own this territory over here. But I'm going to show you how this is a 2014 margin, and I'm going to show you what it looks like now based on the evidence of new expeditions. But you can see these ice streams flowing out. And these two, the Hudson Strait ice stream and the Boothia-Lancaster ice stream, both discharge IRD events that are major big IRD events into the ocean. IRD is ice rafted detritus. So icebergs came out and they were charged with sediment, and they leave a record of instability of the ice sheet, because when you get calving ice, it means that the ice is unstable. So we're going to talk about these, and then we're going to also talk about a little bit about this really interesting thing, which is that when the ice sheets go confluent, this is an Inuitian ice sheet here, the Greenland ice sheet and the Laurentide, they block these channels between the Arctic Ocean and Baffin Bay. And it's only when you get deglaciation that those channels open up and you get an open through flow. Okay, so now getting back to the BBDCs, the reason you have these detrital carbonate events is that all this land in here in yellow is Paleozoic carbonate. So when you get glacial erosion of that land, it erodes the carbonate, and then when icebergs are released, they release carbonate, and that drifts around Baffin Bay. So here you can see this core 59. We know that BBDC1, which was dated at 15,000, is right here in the core. So this is how great cores are. They tell you this is an event and it happened at 15,000 years ago. You can remember a little bit what BBDC1 is, and that the Laurentide ice sheet margin was way back here. Okay, so now I'm going to go up to, this is the next Baffin Bay expedition. It was in 2009 on the James Clark Ross, this ship. And we used swath bathymetry, multi-beam bathymetry, which is really cool because you can get a much bigger swath of the seafloor. And then you're like mowing the lawn, going around like this and getting a beautiful map of the bathymetry. And we took this strategy of going along the troughs and then looking at the trough mouth fans. And that part of the reason for that was that the people that I was working with on this were really interested in the processes of the ice margin. And that's not the best for getting an ocean, like a paleoceanographic record, but it's really cool for understanding the processes. And they found all kinds of really cool evidence that the ice sheet, that these ice streams had advanced to the shelf edge. There's streamlined subglacial bed forms, megascale glacial lineations. And I'm going to show you, I hope you can see these. These are megascale glacial lineations off the Umanak trough mouth. So they tell you that you had fast flowing ice all the way to the shelf edge, and also that the ice dumped off these debris flows off the margin. So we did get a core here that we could get a hemipelagic or a paleoceanographic record from, but a lot of it was, you know, stuff that you wouldn't want to study for foraminifera and things like that. Okay, another really important concept is grounding zone wedges. Here you can see this one here. It's also in the Umanak Trough. It's big. It's so big that you can see it on bathymetry maps. And what it tells you is that there was an ice shelf there. When you have an ice shelf, it tells you that you've got a stable margin. And that's important for the stability of the ice sheet. So the ice margin sat here and smeared sediment out because it didn't have anywhere to go under this ice shelf. And nobody knows exactly how long it was there, but we're actually studying that in one of the last part of this. I'll tell you a little about it. So this is important. It's an important concept that if you have an ice shelf, you have a stable margin. If you have a bunch of IRD and CAV and icebergs, you have an unstable margin. Okay, now I've been telling you about sediment cores. We have to, in order to get the ground truth, we have to pick up these sediment cores, and there's all kinds of ways to do it. This is the vibrocore, which is gently lowered, and you get a camera taking it all the way down, and then it vibrates its way into the sediment. And it can only get 6 meters of sediment, and it has to be less than 2,000 meters water depth. This is on the other extreme, is the Calypso giant piston core. This thing weighs 14 tons, I think it was. And it's a piston core, and it goes lower down and it goes boom into the sediment. And they were able to get really long cores. And we did some projects with these Calypso cores. And then there's all the sediment core processing. I told you about being on a ship, and you do splitting and describing and sampling, and also before you open a multi-sensor track to get high resolution records of different kinds of properties. And here's another, because you don't want to leave people out. This was on the OD 1507 expedition to Peterman Fjord. And these are some people that some of you might know. Here's Kent Simon on the JR 175 cruise, and Mariah Walton. And you can see we have so much fun in the core lab because it's like a sweatshop. You're there, there's never a lack of work. You just are working all the time. And people can get pretty silly in that environment, but you take all these samples and bring them home and start working on them. So this is a funny picture in a way, because we didn't know there was an ice shelf before. And so when these diagrams were made by Colm O'Coffey, he had the ice terminating at the shelf edge, which is correct. And it has all these sediment gravity flows. And you can see the icebergs coming, and that's part of the hemipelagic sedimentation. And so that told us about the ice. That was like the sediment core evidence for maximum ice. And also we had shells and things that we could date. And if you make a debris flow that entrains a shell and you date the shell, then that debris flow can't be any younger than the shell. So it provides some evidence. But this is what those sediments look like. You get debris flows and turbidites. And so there's a limit to what a person like me doing forams would want to do with those. I'm after these hemipelagic sediments, which are having a sequence that where the sediments are laid down through time. And you can see all this coarse material, that's IRD, ice rafted detritus. And I think I've made this point already, but in order to have calving of debris-laden icebergs, you can't have an ice shelf. And that's because of the next thing we'll talk about, which is that ice shelves lose their debris before they calve off. So they calve clean icebergs. So that's already here you have information that you don't have an ice shelf. And here's just to show you how dirty an iceberg can be. And these forams, I can sneak in a couple. That's Ophidium clavatum, and it's a really good indicator of ice proximity, glacier ice proximity, and meltwater and turbid meltwater plumes. So that's an environment that's important in glaciated margins. Okay, the last of our background, Atlantic water. This is a big heat conveyor, and it can convey heat to the ice margins, which is destabilizing. So the Greenland ice sheet is vulnerable to Atlantic water. And this is the part of the project. This is what I work on a lot because forams tell you about ocean forcing. There's different assemblages of forams, and you can also do geochemical treatments to see what is the temperature. So what happens is the Atlantic water comes around and it gets under the ice and it eats away at the ice margin and it can destabilize the ice. Okay, now we're to the ice shelf part. This is a picture from 1977 based on of the LGM maximum of Northern Hemisphere ice sheets based on essentially no data in these marine areas. But it's fun to have this kind of contrast with data controlled more minimum ice. And here in the dotted line, you can see Art Dykes 2003 reconstruction. And once again, on Greenland, we don't have the ice going out far because people don't do both ice sheets. So we don't have much ice and we don't have an ice shelf. I want you to see that there is an update based on these, the JR-175. We do know that the LGM Greenland ice went out to the shelf edge. So that's just an update for that. Here's another ice shelf reconstruction, also based on no data. It's because, you know, you can use a model and it says that if you want to explain Heinrich events, you can make the Hudson Strait ice stream go across and ground against Greenland and cut off the Davis Strait. And since we don't know anything about Baffin Bay, why worry? And then you can break it up and have a Heinrich event here. But we actually had this core 12 PC, which has an LGM record. And we found that the characteristics of that core didn't allow us to have the Baffin Bay sealed from the south because there would be nothing going in for food then. And so we decided that the 12 PC record sediments said, no, there's no embayed ice shelf. But actually 12 PC did support a fringing ice shelf. And so this is the reconstruction that we did. And we did see evidence of ocean forcing that drove the ice sheet off the shelf edge. And it stabilized for a while to make a grounding zone wedge before it calved back. And Greenland and the Lancaster Sound ice retreated. Okay, so we were kind of guessing about these ice shelf sediments, and but we had this opportunity to go to the Petermann Glacier, which has a floating ice tongue, and look at the characteristics of sub-ice shelf sediments, because we had a drill that could drill through. And so what you have here is, I just want to give you an encapsulation of what sub-ice shelf sediments look like. Because the ice shelf is a debris filter, and that basal sediments are melted out at the grounding zone,
you don't get IRD. It's really dominated by meltwater plumes because it's a meltwater system. And there's hardly any food, so there's hardly any forams. And this species that I showed you earlier, Alphidium clavatum, doesn't go under ice shelves, and it doesn't go under perennial sea ice either. It only likes to be with the IRD. So now I'm going to show you, where that is. So here's the Peterman Fjord here. Remember I told you that this was a channel that was blocked by confluent ice sheets. This is the Nares Strait. Here you can see that the Greenland ice sheet and the Inuitian ice sheet went confluent and blocked it at the last glacial maximum. And what happened here is that there were two big calving events, which opened up the seafloor so that you could bring a ship in and look at sediments or the part of the fjord that had recently been covered by an ice shelf. And because we had this bedrock drill, we could also take cores through the ice shelf and pick up the sediments that were still under there. And that's what this is. This is Kelly Hogan and Peter Washam. They're capping off this sub-ice shelf core. And this is what the system looks like as it's going through. They use a hot water drill to drill all the way through the ice shelf, and then they can take a core. And if you look, these are two pictures, one from the bottom and one from the surface. This is turbid meltwater right at the top. Right as you get below the ice shelf, there's all this sediment in the water that's very fine grained, and it's a turbid meltwater. And then as you get down to the bottom into the Atlantic layer, the warmer Atlantic water, the sediments have flocculated and they're depositing as clumps. Is that twice? Or did I not show you that? Anyway, that's what I was talking about in case I was not telling you what I was looking at. Okay, so this is what the sediments in these two cores look like. This one here is in front of the grounding zone. And so it's exposed to that energy at the grounding zone where meltwater is coming out and making turbidites and plumes. So you get these rip-up clasts, which tell you there's a lot of energy there. But there's no IRD to be seen. And this one is on the sill. So it's protected from that energy of the grounding zone. And there's enough food coming in that there's biota that's burrowing this area. But there's no coarse material at all. And this is so you might find this surprising, but this is what we saw all over Hall Basin, which we went and cored extensively in. And we're like, how come we have all this laminated sediment with no coarse material in it? We thought about that for a long time. And suddenly it dawned on me that it's because these guys end up looking like the ice shelf sediments. And we had these two ice streams with ice shelves coming out, and you had Atlantic water swirling around. The subglacial meltwater was coming out and left all the coarse material behind. And also there was all this topography. And we end up with tons of this laminated stuff. They called it the terracotta lipstick. It's just clay. So, and it was beautifully laminated. And in fact, this is the event. You see this laminated sediment, then there's an IRD layer, and then you have bioturbated mud. That is recording. Here we have the two ice shelves. They break up, and that opens the strait, and that's the end of this sequence. That's how cool sediment cores are. They tell you the story that happened. Okay, this is the last part. This is about BADX, which is the Baffin Bay Glacial Experiment. Robert went on this cruise as a representative of INSTAAR. And we were studying the timing and triggers of Greenland ice sheet retreat from the last glacial maximum. And the area that INSTAAR has coursed from is here off the Umanak, which is the place that I showed you has the big grounding zone wedge and the megascale glacial lineations. So before we had even, before we got our funding, this paper came out. And then before the cruise, this one came out. So a Baffin Bay ice shelf, two kinds were proposed. One was based on evidence of ice shelf moraines right here. And the other was based on evidence of ice shelf moraines here. But they're quite schematic, these maps. They don't have very much data. They did both honor this 12 PC idea in southern Baffin Bay that it was only a fringing ice shelf. So that's why they stop where they stop. Meanwhile, Shannon Klotzko, who's one of the PIs on this BADX project, she has mapped all around the margin looking for all of this evidence for an ice shelf. And she comes up with what she calls the ice contact boundary. And you can see it's deepest here, and it shallows towards the front of the ice shelf. And INSTAAR is working here in this very complicated area where you're near the front of this ice shelf. And we have three cores. One of them is in this Umanak trough, where which is right before the grounding zone wedge. And we've got a date now that says that the ice margin in Umanak had retreated almost to the grounding zone wedge by 15,700 years ago. So that was really surprising to me. This core can you see these ridges here? I don't know if you can see them with this light, but this is the ice contact boundary. So our core 71 had the ice shelf sitting on it. So that's kind of a funny core to be getting, but it's really interesting. The one I'm going to show you today is this one, 66, which is supposed to be in the ice shelf cavity. So below this ice contact boundary. And here you can see it again. Here's the ice contact boundary. And then here we are in the ice shelf cavity. And you can see there's this big transparent unit. And this, we know, I'll show you evidence of it, is BBDC1. So we know this is at least 15. And we went into this transparent unit and some others. Despite the fact that we tried to go to the north of the trough mouth fan, we still got gravity flows, which I guess is the way it is with an a glaciated margin. But first, take a look at 66. These are the CT images. You don't see any coarse material in here. There's nothing coarse until you get here. And that's what these IRD counts say. So that's in support of ice shelf sediment. When you there are a couple places where there's these little peaks in carbonate, and then you get to the BBDC events here, and we've dated those. And you can also see that, I don't know if you can see it, it's really small on my screen here, but it looks like you see Greenland deglaciation, no carbonate, and then you get the BBDC events. So we're still building this record, and I have been working really hard trying to get dates from these. And I'm going to show you this briefly because it's too hard to explain in short time. But we have in this core 66 a beautiful sequence that shows, this is the possibly glycogenic debris flows down here, but a species that doesn't really that doesn't record meltwater, a species that records perennial ice, a species that records glacial meltwater, and then this productivity interval. And then above that, there's hardly any fauna because it's all dissolved. They're all dissolved and you only get the agglutes. And I'm going to show you my spectacular assemblage. So these, well, for me, this is like the most exciting thing I ever saw. These guys I have never seen before, and they're called Orchidia riedeli. And they're a species that occurs in temperate to subpolar waters, or that's also been said tropical to polar waters of enhanced productivity. So this one and this one, which is Polinia boloides, which comes into play in the Denmark Strait, between Iceland and Greenland and north of Iceland, when you have Atlantic water coming in. So these two are telling us that we have a lot of productivity, and we're probably getting an encroachment of Atlantic water and meltwater coming out, and that's creating this highly productive environment. And these are probably telling us about the beginning of the end for the ice shelf. So that's a close-up, and there's also a lot of volcanic glass in here. So in summary, I want to say this is John's expression. Science is a series of approximations, which is sort of what we have here so far, but we're gonna find out. We have good evidence for a Baffin Bay ice shelf. And we're gonna keep exploring it. When did it advance? When it retreated, and how fast that happened. We already know it was back in the Lancaster Sound by 15,000. And we want to get more details on the ocean forcing. Thanks for listening.
Time for questions, and I think some folks are monitoring Zoom for that.
So just speak up and we can talk to the owl center.
Nobody has a question? Okay, Tom.
Can you say something about how the triangle event correlates or not to Heinrich one, and whether retreat of the ice shells is important for Heinrich events or irony events?
The BBDC event postdates the Heinrich event 1. And it's a little tricky because of the reservoir ages and other things. So in this project, we have a really great, we took a core off of the Labrador margin that has Heinrich events in it. And they're doing I've done the dating, and they're doing the PSV, the paleomagnetic signal. And then we have our cores in Baffin Bay. And that will be more of a synchronizer, the PSV, because you can align any of the paleomagnetic signatures with one another, and then maybe have a way of looking at the dating.
Does the fact that the Baffin events come later, is that explained by just the ice shelf continuously retreating into Baffin?
That would certainly be one hypothesis, because, well, we didn't even know we had an ice shelf until, so people have been working with not all of the knowledge, but and then the other thing about the BBDC events is that there's another source of them, which is Home Bay, the Home Bay ice stream. And so people have been, it's a terrible practice, but just counting them wherever they are, counting them down their core. So you have like several BBDC2s. You don't know which one you've got. And so it's driving me nuts. And I think we have to have people, if they have new cores, they should say which count it is with that core name after it, so that you know which, because eventually it'll be shown that some are only occurring south of the ice shelf and some are coming axially as the bay deglaciates. Anybody else?
Yeah, I mean, you worked in Antarctica as well. I wonder whether there's any lessons that you learned from Antarctica that we can transfer to the northern hemisphere.
Well, one of the things that's I think is most interesting about the Antarctic record is, in Antarctica, there's not much meltwater, although there's more meltwater seen now, looking like under Thwaites, for example. And so you don't get these meltwater facies. And the meltwater really drives. It's the subglacial meltwater. It can come from the surface and down to the base, when it rises up at the grounding zone, it's terribly erosive to the ice. So that is a real threat for Antarctic ice shelves. And it's a growing threat. I think people are starting to see more and more. I think it's really cool, actually, that, there's these gigantic ice shelves like the Ross Ice Shelf. And it has a null point. So the whole basin is just full of mud, all this laminated ice shelf facies, and it's all plumes from meltwater plumes. There's the sediments come out and they peter out before they get to the edge of the ice shelf. So you get this null point where there's nothing. Stuff could be coming in from the edge, advected in, stuff could be coming from the grounding line, and there's nothing, they don't meet because it's too big and there's not a lot of meltwater. So I think that's part of the reason why there's these ice shelves are still there, is that there's not a lot of meltwater.
I have more general questions about, you're saying that ice shelf filter the IRD out.
Yeah.
So how do we get ice rock to breeze like off through like this Iberian margin?
Well, those are, so if you don't have an ice shelf, so once, let's say you had an ice shelf and you broke it off, then you get this out of control calving. And the calving happens so fast that the basal debris is carried out. Boing, it goes out. Then it melts as it reaches warmer waters and it gets distributed widely.
So it doesn't come out under the line when the ice shelf is just retreating really fast.
Then it's not melted out. Some of it probably is. And there's less of it as of the basal debris as you get farther away. But but that's how you get those far traveled icebergs, like the IRD belt of Ruddiman. That was from far traveled icebergs that met warmer water and preferentially melted their debris there. No other questions? No one wants to ask about borams? Sylvia.
I don't know anything about forams, except that they're useful and cool. But a couple questions. One is, you've employed like generations of undergrads.
Yes.
And do you train them to identify the foram? But are they like,
Yeah.
is it hard to tell them apart, or are there lots of like subtleties about this?
There's a lot of subtleties. There's a lot of training, and that's why I don't ever want to get somebody who's already a senior. Because then I don't get a payback. But
The next question is, how do you figure out which forams grow where? Like, are they all still existing?
okay, well, thank you for asking that, because I could have put that in here. I've done quite a few modern studies where you can sample an environmental gradient of the surface sediments. And in fact, we did one for the Peterman. We got samples from under the ice shelf and out into the mobile ice belt. So under the ice shelf, in the fjord, and out in the Hall Basin. And I've done some around Iceland, and another project on East Greenland. And these are really useful because they tell you, you took this sample, this is the environment it's in. And the Peterman one is probably the best one I did, because when you go to Baffin Bay during the glacial, that's the assemblage you get. So it's very recognizable. But there's other proxies now, like Julio and Robert are using the biomarkers. There's always new proxies that are helping us to do a better job of reconstructing the environments. Robert?
Are you getting a regional picture of possible ice re-advance during the younger dryas?
So are you thinking about the grounding zone wedge, or
Yeah.
the pause in the pause between BBDC?
Yeah,
Soon.
yeah, potentially.
Soon as we get these dates back, I'll be able to tell you more about it. But yeah, it's interesting. The dates are needed because I don't know. But it looks like, I feel like the big grounding zone wedge was stable there from like 15 something to the end of the Younger Dryas when it retreated. I think that's going to be the story, but I don't know for sure till we get the dates. Astrid.
And that was a wonderful talk. So first of all, thank you so
Oh,
much. I enjoyed it
thank
so
you.
much. I'm sure everybody else did. When I first joined INSTAAR and we started working together, which was so wonderful, I learned so much from you, and I learned about these things called forams, which were new to me. And I also learned through you a little bit about diatoms, and you taught me a mantra, which was diatoms are plants.
Oh, yeah.
And so here's my silly question. Forams, yes, and we can learn a lot from them. But what about diatoms? You didn't mention them today. Do
Well,
they figure at all in this kind of research now?
well, as Robert knows, in Baffin Bay, there's this giant diatom. It's giant in a micropaleo sense. It comes in the sand fraction. And it tells you when you get all these diatoms preserved, there's a ton of silica around. And they are just exported to the seabed and not dissolved. And sometimes there's so many of them that we have to float the sample in a tube and send them out into a filter so we can catch them. And we actually were measuring the silica in them and everything. But they've been called Cocinodiscus oculus iridis, but that isn't what they are. And Sarah Spalding is working on this. She's trying to figure out what this species is, but it is an indicator of stratified water column. It's often associated with things like Arctic surface water that are rich in silica and glacial meltwater, which must also have silica. And so we see them and they get in the foram samples because they're sand sized. They're really big. Most diatoms are drained down the drain in my mud, the finer fraction. Yes, and diatoms are plants.
Suzanne has a question online. Suzanne, Sheila?
Go ahead, Suzanne.
Unmute. Oh, I did. Okay, now I'm unmuted. Can't start my video, but oh well. I'm just perking up at the thought of all this silica. My work on glaciers and weathering is that they tend to be quite low in their silica fluxes compared to, non-glacial streams. So I'm just, it would be, yeah, I just want to. I'm quickly responding to the idea of there being these giant diatoms that are feasting on all this silica. I'd be surprised if it was coming from under the ice sheet, but
Do you
maybe I'm
think it
wrong.
might depend on what the bedrock is under the ice?
I mean, the argument goes that it's pretty cold underneath an ice sheet, and that tends to damp down the weathering rates. Whereas we tend to see dominant solute fluxes dominated by minerals that are very easily weathered. So carbonates, any sulfides, pyrites that very quickly oxidize. Things that happen really fast, you see those dominating the solute flux.
Well, that's interesting, Susanna. I don't know the answer to that. I just know that we get these diatoms. So we see them come in really high numbers when those channels open to the Arctic Ocean. And then we also see them on the deglaciating margin, but not in as high abundance because it's a flux. I don't know what the flux is, but there's a lot more sediment, glaciogenic sediment coming in. So I don't know. I was sort of inferring that, but I don't know it.
Yeah, interesting. I mean, all my work has been on alpine glaciers, not on ice sheets, and so maybe there's something a little different in that setting. And it's also I'm talking about kind of proportions as well, rather than actual fluxes. So that might be a difference.
Yeah. Anyway, they are present and they're large.
Cool.
Valerie.
Yeah. Ice shelves on northern Ellesmere Island So I guess they've been breaking up for, I guess, more or less different reasons, I think, but not water low. But so I got to work in the Disraeli Fjord back ages ago, 1987, I think. And so there was the Disraeli ice shelf, and it had only a little bit of melt in the summer on the surface. The fjord was covered with 3 meters of ice. And as a side note, we were able to core sediments from 180 meters using Mel Reisner's percussion.
Oh.
So we augured through 3 meters of ice, and we pounded it, and we got 3 meters of sediment that we hauled out with a snowmobile.
Nice.
14 tons. So different. Anyway, so I was teaching in 2008. With you looking for photos online of the fjord as I knew it, and it was always pictures of open water,
Oh,
which was a shock.
yeah.
Okay, this is happening. And then the ice shelf was breaking up, and I'm just wondering if you know about how that happened, like what was going on, because they called it a freshwater lake. And so I think freshwater that was abutted up against the ice shelf from melt, from the water that was high, the water column. And I wonder if that maybe contributed somehow to the breakup of the form temperatures.
I'm not totally sure about that ice shelf, but a lot of those northern Ellesmere ice shelves are sea ice shelves. They're perennial sea ice that have become ice shelves, but they don't have the same dynamics as a floating ice shelf or tongue from a glacier. And I think warming has just destabilized these, and that you get less sea ice, more mobile ice in the Arctic Ocean, and then there's more forces that are just bringing corrosive or erosive warmer waters to the ice and making them go away, and strong wind.
Maybe one last question. Where are the ice shelves today that you can draw parallels to from the Baffin LGM shelf? What might your research tell us about their behavior as the climate warms?
Well, I have a slide that I took it out of the size of the Baffin Bay ice shelf. It's a similar in size to the Antarctic ice shelves of today. It's smaller than the Ross, bigger than the Amory. And I think it came up before. Meltwater is death to ice shelf. So as we have warming, I think the melting, subglacial melt is going to be making those ice shelves more unstable. And then once the grounding line retreats off of these negative slopes, then we'll have a BBDC event of the Antarctic type.
The Antarctic ice sheets, there's something like 250 subglacial lakes.
Oh, wow. So we could have some of
And
those too.
so is there any way of distinguishing, when you say meltwater? Do you know it's meltwater, or could it be a subglacial ice just draining rapidly?
I think it could be both. I don't know. I haven't done anything to tell me about that, but there is that big canyon along the Peterman drainage that suggests there might be water, or it was carved by water, but I don't think anybody has seen a lake, a subglacial lake or anything there.
Well, we've hit the hour, so let's thank our speaker one more time. Come back in 2 weeks for the last semester.